Hello friends, welcome to my channel. Let's have a look at problem 270, closest binary search tree value. In this video, we're going to share two formats of solution. The first one is based on traversal, and the second one is based on recursion. First, I will read through Hello friends, welcome to my channel. Let's have a look at problem 270, closest binary search tree value. So this is actually an earlier problem, and it's also marked as easy. So here our purpose is to practice with the binary search tree data structure. In this video, we're going to share two formats of solutions. In the first solution format, we're going to use a traversal, more specifically in-order traversal, and then we do a binary search. And in the second solution format, we directly do binary search during the traversal. First, let's read through the statement. Given the root of a binary search tree and a target value, return the value in the binary search tree that is closest to the target. So in example 1, so we have this tree as target is 3.71. So we can see that the root 4 actually is closest to this value in the sense of absolute value, right? So the output is 4. In example 2, so this is actually a very special one. The reason is that this tree is a single node tree, so we can only return the root value. So this is the main statement. The constraints on this problem are the following. First, the number of nodes in the tree is in the range given by the closed interval from 1 to 10 to the power 4. In particular, this tree is not null. And secondly, 10 to the power 4 gives us the problem size upper bound. And secondly, the node value is bounded below by 0. In other words, it's not negative. And the target value, on the other hand, can be negative, right? So that's the constraints. So with that said, so we are ready to look at the code. So here, due to the simplicity of the logic, we are not going to write the methods or do walkthroughs. So here we are going to give two treatments. So the first one actually is based on in-order traversal. So plus binary search. So this binary search would be a vanilla binary search. And in the second one, we are going to do binary search in the context of BST, binary search tree. So in other words, it's more adapted to the data structure. So here, let's first write the first format. So V1, so in-order traversal. The reason we're doing in-order traversal for this problem is that due to the binary search property, an in-order traversal of the binary search tree gives us a sorted list from small to large, right? So for this purpose, let's first write the in-order traversal hyperfunction. So this is actually very routine or standard. Let me write like this: define in order. So we're going to put a node. Say let's put root here. So if not root, so we're going to return empty string, empty list. Otherwise, we're going to return. So let's do some self-calls. Root left plus the root value plus in order and apply to root right. So this way, this function gives us a in-order traversal. So the result will be a sorted array. So a list. Let's call this list array. So once we are here, actually we can do binary search to find the nearest value corresponding to the target. So here, let me use a binary search method called bisect, bisect right or left. Both are okay. So here I'm going to use bisect left. So IDX, so this is going to be an index, bisect left. So bisect left. So the array we are searching for is array, and we are searching for target, right? So it's possible that the target is in the array or not, right? So here let's consider several cases. If idx equals 0, right? So in other words, the target compared to the element in the array is smallest. Then in this way, we are going to return array, the first element. Another case is array equals n minus 1. Let's introduce an n. N is the length of the array. In other words, the number of nodes in the binary search tree, so or in the BST. So if the ID equals n minus 1, not n minus 1, it's m. It means that compared to the elements in the array, so target is largest. So in this case, we are going to return array -1, right, the last element. So these two cases are the two edge cases at the two very ends. So in general, so if array, so we need to consider idx and idx minus 1. We compare which two of these values are near to the target, right? If array idx minus target is less than or equal to target minus array idx minus 1. So notice that we are using bisect left. It means that left to this idx, all the elements in the array is strictly less than target, right? So this way, if this is near, so we're going to return array idx. Otherwise, we're going to return anyway. So array idx minus 1. So this is always true, or can always be checked. This because we have treated idx equals 0, and this idx minus 1 is always can be checked. Always can be checked. So that's the first version. So now let's do a check. Solution has no attribute closest value. So here I'm going to change this function name. So now let's do a check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. This is version 1. So now let's so this way, though we used the binary search, but we actually take a long way. So we first get the corresponding sorted list. In some sense, a serialization of the tree, and then we do the search. So actually, we can do the tree to the search on the air. So let me copy this function signature comments. So let's do a second version. So let's call this one version 1. So now the version 2 is binary search. So pure binary search, but we adapt it to the binary search tree data structure. So here first let me initialize a result, so to be root value. This can also be always initialized. The reason is that the number of nodes in the tree is bounded below by 1. In other words, this tree represented by the root is not null. So once this initialization is done, so we can do a while loop. So while root. So we're going to compare the result, so update this result. So we want to see if which one is near to the target. So actually we can use absolute value to compare, use if and else, or we can do something like this. So the root value, so this is the current root value, right? And the previous result. So we compare the previous result and the current root value, which is near to the target. So this corresponds to a key for taking minimization or operation. So here is a lambda function x. So we're going to so check target the distance of x with respect to target, right? So then what we're going to do is to check if target equals root value. So this is actually a very special case. In this case, actually we just need to return the root value. So notice that here we need to return root value rather than the target. The reason is that the target is float and the root value is integer. So in such a sense, we do not need to check this condition. So now let's write a little bit different. So let me do this. If target is less than root value, what we are going to do is because target is smaller than root value, so we are going to move to the left in order to make the root is near to the target. So root equals root left. So in all the other cases, right, so we're going to move to the right. So this is the way we actually do this. So actually we can put a else if block checking target equals the root value, but it's not necessary. So with that said, so we're going to do the return. So we're going to return the result. So this actually is in essence the same as the first version, but it's more succinct in some sense. So with that said, let's first do a check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So I guess that's about it for this easy problem, and it's also about it for this video. Thank you.